Let's do some examples related to the improper integrals now. We'll start with the integral of 1 over x from 1 to infinity. So what we can do is, since we have an infinity in the upper limit, we can call it as an improper integral type 1. And how do we solve these types of integrals? By this formula as I described in the previous video, right? So what we have to do is we should simply consider it as a limit problem where you have the same lower limit and the variable t as the upper limit, and you have to get the limit of t goes to infinity, right? And you just have to solve this integral, which is a definite integral. Now when you are computing this integral, we consider t as a number, right? So then the calculation will be like this. The integral of this one is ln x, and when you substitute the two limits, I mean the upper limit and the lower limit, you will get this one. And remember, ln1 is equal to 0. So the answer will be the limit of ln t when t goes to infinity. Where now to compute this one, you can even consider the graph of ln t, which is like this. Okay, so this is the graph of ln t, and this is the intersection point. So you can see when t goes to infinity, now here don't consider the area under anything, okay? Just consider the values of ln t, right? Because here we don't have any area notation, it's just the function value. And looking at the graph, you can see when t goes to infinity, these values will eventually goes to infinity. So the answer will be infinity. In other words, this integral is an improper integral. No, it's anyway improper because of this infinity in the upper limit. What I wanted to say is, since the answer is infinity, this integral does not converge. In other words, it diverges. So the idea that you can get from this conclusion is, if you draw the graph of this function, it will be something like this, okay? And starting from 1, if we compute the area starting from 1 and goes up to infinity, if you compute this area, it will be a infinite value, right? It will be a very large value, right? I mean, what I mean by very large is, it cannot be represented by a finite number, right? No matter how large you write, it will be definitely larger than that finite number. That's the meaning of infinity, okay? Right. And then we'll go to another example. How about this one? Now this is the same thing that I went over in the previous video also. Now the difference between this one and the first problem is, here you have 1 over x, and in the second case you have 1 over x squared. So when it comes to 1 over x squared, you can see, like, as we have infinity in the upper limit, this is an improper integral type 1, and this is the way that you should solve that sort of an integral, as we explained before in this green color. And you can see, by simplifying it accordingly, the answer for this one is a finite value. In other words, this improper integral converges, right? Now this is a very interesting result, okay? Because now the graph of 1 over x squared is almost the same as it is for the graph of 1 over x, right? The shape is almost the same, right? But see, now if you consider this one, and if you consider the area, from the above calculation, from this calculation, we can see that the area of this infinite region is a finite value. And from the first calculation, we can see the area of this region is an infinite value. So the only difference is that the two functions are different. So in conclusion, what we can say is, although the shape of the two curves are similar, there is a difference after all. Okay, so in other words, the area that 1 over x covers is very much larger than the area covered by 1 over x squared. That's the conclusion that we can get by comparing these two problems. Okay, right. Now let's move into the third problem. It is, now in this case you have negative infinity as the lower limit. So again, by considering our definitions, we can label this integral as a improper integral of type 1. And to compute this integral, we use the part B of this green color note. Okay, so here we have negative infinity and t goes here and the original upper limit goes here. Okay, so we should apply the same thing in this case, right? Now by computing to compute this integral, we will need integration by parts. Okay, and from that you can obtain this as the answer for our definite integral. Now I haven't written down the steps for integration by parts. Okay, it's up to you. Like it will be a good exercise to calculate do this simplification, right? And you can see for this limit you have 3 terms, right? So we can distribute this limit across all these 3 terms, and for this one you can like another property of limits is, if you have minus fx, you can take that minus sign out from the limit. Okay, so in both these cases you have a negative inside, so you can take it out from the limit symbol, right? And for this one you can see that the limit, we are taking the limit of t goes to something, but here in this function you don't have any t value, so this limit does not do anything for our function inside the limit notation. So simply the answer for this particular portion is equal to 1. And for this one I think the easiest method is to consider the graph of et, right? If this is t, now you should be familiar with the basic graphs of these functions. Okay, so graph of et will be like this, right? Now this is et and the intersection point is 1, right? And see, if t goes to negative infinity, the value of the function will go to 0. In other words, the answer for this one will be equal to 0. How about this one? Now we are taking the limit of negative infinity of this case. Now if we just consider the values of t and e to the power t, when t goes to negative infinity, t will be negative infinity and et will be 0, right? So we cannot directly substitute the values and see what will happen. So what we can do is we can use the L'Hopital's rule. Remember in calculus 1 we did a thing called L'Hopital's rule, where if you have a rational function like this and if you need to compute the limit, and when computing the limit, if you get things like this, right, these kinds of inadmissible situations, we can use the L'Hopital's rule. So what does the L'Hopital's rule say? The limit of this original rational function, this or limit of this quotient, because when I say rational, normally we have polynomials in the numerator and the denominator, but here for the L'Hopital's rule you don't need to have polynomials, right? You can have any function that you prefer. Okay, so if you get a absurd result like this just by substituting the value, L'Hopital's rule says that you will get the same limit when you have the quotient of the derivatives of these functions, right? So simply you just write down the derivatives of numerator and denominator and get the limit, and this limit and this limit should be equal. So if you cannot directly compute this limit, go to the derivatives and compute the limit, so it will be the answer for this one as well, right? So what we are going to do is we try to adapt L'Hopital's rule for t times et, right? And to apply L'Hopital's rule we need a fraction somehow other. So we should try to see this t times et as a fraction. Okay, so what we can do is we can write it as e over e to the power negative t, right? And then to apply the L'Hopital's rule, if we differentiate top and the bottom, now don't mix it up with the quotient rule of the derivative. Okay, quotient rule of the derivative says something else. Now we are not applying the quotient rule anywhere in this L'Hopital's rule. Okay, what we simply do is we just differentiate the numerator and differentiate the denominator separately. Okay, and then we get the limit, right? So the limit of this one is equal to the limit of this one, t goes to negative infinity, and from L'Hopital's rule it says the limits are equal, right? So then you can see the limit of t goes to negative infinity is equal to this, right? Which is e to the power t, right? And that will be equal to 0, right? Now here you have negative t in the denominator, so you take it up, so it becomes e to the power t, and here we have t goes to negative infinity, and it is the same case as I explained in the in this third term, right? So this answer is 0, right? In other words, our integral, our improper integral, this one will be equal to 0 minus 1 plus 0, which is equal to negative 1. Okay, and since this is a finite number, we can conclude that our improper integral is convergent. Okay, so this is also convergent. And finally we will compute this integral. Now you can see here you have infinities at both lower and upper limits, so that goes with the third part of our improper integral type 1, which is this one. And remember I said for this equation to make sense, both these integrals should be convergent, otherwise we cannot write this equation. So in order to compute such an integral with infinities at both lower and upper limits, first we have to find out two convergent integrals of this nature. That means if we consider the example that I have written for this one, let's say a is equal to 0. We'll start with 0, but it's not a must. Okay, So what we can do is, instead of writing the equation at the very beginning, writing this as 0 to infinity plus negative infinity to 0, instead of writing the equation at first, what we can do is, if we are doing it in a very precise way, what we can do is, we will get rid of this equation, and then we'll first compute the required two improper integrals separately. Okay, we'll consider this one and we'll try to compute this one separately. Okay, and if both these integrals converges, then we can write down the equation, because that's the correct way of evaluating this integral. Okay, so we'll do it one by one. So if we compute the two areas, the integrals separately, we can see that when you have 0 as the lower limit and infinity as the upper limit, the integral will go like this. And then from here, now remember, the integral of this one is equal to tan inverse x, which is a standard result, right? It's kind of a standard result, because if you differentiate tan inverse x, you can see that you will get this 1 divided by 1 plus x squared term, right? Okay, so now accordingly we will get tan inverse t minus tan inverse 0. A good way to understand the values of these terms is by drawing the graph of tan theta, right? The graph of tan theta will be like this one, right? And here you have 90 and here you have negative 90, right? They are vertical asymptotes. Okay, so this is tan inverse, so we should consider the inverse of this function, right? Now in other words, if you consider this one, what is the suitable x value for y to be 0, right? That is 0. That means this is equal to 0, right? Tan inverse 0 is 0. And how about this one? Tan inverse t when t goes to infinity. In other words, what is the suitable t value so that tan t is equal to infinity, right? That's the meaning of tan inverse t. So if we just substitute this one, it will be tan inverse infinity, right? So we need to find this suitable t value so that tan inverse infinity is equal to that t value. So what should be the suitable t value? That will be pi by 2. See, if you substitute theta as pi by 2, you can see tan theta will go to infinity, right? So this will be equal to pi by 2. And similarly for the other direction, for the second integral, you have negative infinity as the lower limit, and by computing these values, do it carefully, because you have 0 as the upper limit and t as the lower limit. So when you substitute those limits, 0 should go first and minus the lower limit. Okay, that's the way we do the substitution for that's the way we substitute these lower and upper limits for the integrals, right? And then here we get for this one we make use of the similar argument, which is equal to 0, and for this one we should substitute t equals negative infinity, right? This is basically finding something like this one, right? So what is the suitable theta value so that tan theta is equal to negative infinity, right? So what is the suitable theta value? And by looking at this diagram, you can see when theta is equal to negative pi by 2, tan will go to negative infinity. So the answer for this one is equal to negative pi by 2, but that comes with the negative sign in front. Okay, so the total result will again be pi by 2. And as a conclusion, we can say both these limits has finite values. In other words, both these limits converges. Therefore, we can write our relationship like this. Okay, so now as we have this relationship, we can get the answer for the given integral as pi by 2 plus pi by 2, which is equal to pi, right? See, now for this function we are actually computing the area from negative infinity to positive infinity, but still it is a finite value. These are very interesting results, right? If you plot this graph, it will be something like this. Okay, it's kind of symmetric. So although we consider both these infinities, so it's like it's not obvious, okay, because we have infinity in the negative direction as well as in the positive direction, but still this area is equal to a finite value, which is equal to pi. Okay, right? And in the next video I will present some sort of a theorem for type 1 improper integrals, and that's it for the type 1.